So we're going to talk about ionization energy in general, and we're going to talk about primarily first ionization energy. First ionization energy is just the amount of energy it takes to remove an electron from an atom in the gas state. So even if it's like a metal, you can vaporize it and form a gas, and then this is the energy it's required to make the metal ion that's in the +1 oxidation state, so +1 state, which means you remove an electron. So ionizations are endothermic in general. Okay, that is, I have to knock an electron off, which means I have to absorb energy, so it's going to require energy to knock the electron off. The first ionization energy for, let's say, calcium, and you know calcium normally makes a +2 ion, right? But we take calcium in the gas phase and we add energy to it, and we'll call it IE1, first ionization energy. And that's going to form calcium 2 plus, or 1 plus, plus 1 electron. Now, this isn't the normal, and again, it's in the gas state. This isn't the normal ion for calcium, but this is what the first ionization energy is. It's just how much energy it takes to make the +1 ion. Now, if you wanted to do the +2 ion, right, then what you'd have to do is do the second ionization energy. And in fact, you can do a third or fourth or fifth. It just takes more energy to do that. But the second ionization energy for calcium is starting in the gas phase from the first ionization, right, plus the second ionization energy. That makes Ca2 plus 1 electron. Now, you'll notice that these ionization energies are for successive ionizations then. If you want the total ionization energy for the entire process to go from calcium to calcium 2 plus, what you end up having to do is add these two reactions together, and then the ionization energy in total would be IE1 plus IE2, like that, right? Let's say we're talking about oxygen, right? Because oxygen normally makes negative ions. Oxygen can be done the same way. I have oxygen, right, and I add in the gas phase, and it's for atoms, by the way, so not O2 in this case, but O, plus IE1. That's going to form O in the gas phase as a positive ion plus 1 electron. That would be the first ionization for oxygen. So ionization energy is always for the formation of a cation, not sort of the naturally occurring ion for that element. Okay, and it's done also in the gas phase, and that just helps to simplify the analysis because there's no other effects that we have to think about going on. So we're going to look at both some specific trends and general trends, but the general trend is its highest to the right on any period, and the simple answer for that is increasing effective nuclear charge. So as the effective nuclear charge goes up, the attraction to the electron goes up, and then it gets harder to take the electron away, right? The other, again, that's a if you're thinking back, that's a Coulomb's law type effect as well, right? You're increasing charge. Increasing charge means higher attraction. It's also Coulomb's law along the group. And if you think about atomic radius, right? And we're thinking about orbital sizes, so we're like 1s, 2s, 3s, and we'll ignore all the other orbitals for now. But the general trend is still true. The higher the principal quantum number, the larger the orbital. Well, attraction to the nucleus is in part based on distance from the nucleus and the effective nuclear charge. So all the 1s, 2s, and 3s orbitals experience +1 effective nuclear charge or +2 effective nuclear charge, depending on if you're in group 1 or group 2. So the deal is that 1s is closer. The effective nuclear charge is the same as the 2s. And if you remember Coulomb's law, right, the energy of attraction is essentially a constant times Q1 times Q2 over the radius. Well, r is much smaller for electrons in the 1s orbital than it is in the 2s. And so in general, the highest attraction is at the top of the periodic table because those are the lowest principal quantum numbers. Okay, so what does the ionization energy trend actually look like? This is first ionization now. It looks like this. And you'll notice the noble gases, as you might expect, being on the far right are the highest. The alkali metals, which are on the far left, are the lowest, and this actually sort of reflects the radius trend. It looks very similar to the trend in radius, and that's because they both depend on distance from the nucleus, right? Because that's the radius, and that affects both the ionization energy but also the attraction of the electrons to the nucleus. And it also shows this sort of increasing trend going from left to right because remember the radius gets smaller as you go from left to right, and it gets smaller because the effective nuclear charge is going up. So really what you're seeing here is a direct effect of the effective nuclear charge. Now, there's a couple of unusual things that are going on in here. So what I'm going to do is I'm going to go ahead and write in the elements for the second period. So I have lithium, and then this is beryllium, and this is aluminum, or sorry, boron, carbon, you notice nitrogen, oxygen, fluorine. And you notice there's a dip between nitrogen and oxygen. Now, sodium goes magnesium, and then aluminum, and then sulfur. Oh, sorry, not sulfur. Silicon, Si, and then phosphorus, and then sulfur, and then chlorine, and then argon. And you notice what happens between nitrogen and oxygen, there's this switch. And is there also between phosphorus and sulfur, and also between beryllium and boron. Okay, so let's sort of take a look at those atoms in particular a little closer, and we're going to jump back to our periodic table to do that. So if we're looking at where we're seeing the sort of anomalies, right? It's actually between beryllium and boron, magnesium and aluminum, and the other place is nitrogen and oxygen and phosphorus and sulfur. And so it's actually happening in the same place on the periodic table in the different periods. And if you look back, right, you can actually see that effect quite a ways down the periodic table, even though you're adding the transition elements. So this is fourth period, so ignore the transition elements, right? There's not a big drop, but there's still a drop here. And then there's going up, and there's still a drop, and there's still this jog between the third and fourth elements in the P block between those on those periods. So let's look at why that takes place. Okay, so we've looked at the left to right trend. That's effective nuclear charge. That's the general trend, right? It's increasing, ionization increases from left to right. And from top to bottom, it changes because of the increasing principal quantum number. So the orbitals are getting bigger, they're further away, they're easier to remove those electrons. Now we're looking at the irregularities that happen from left to right, and to do that what we'll do is we'll write the electron configuration. So for beryllium it's 1s2 2s2, and for boron it's 1s2 2s2, and then 2p1. Now if I look one row down, right, I have magnesium. And I'm just going to do the outermost electrons now. It's actually 3s2, and then aluminum, it's 3s2, and then 3p1. And you'll notice there's an energy, a cost associated with putting electrons in the 3p or the 2p orbitals relative to the 2s. Now the reason for that is pretty straightforward, I think. Remember when we were doing Aufbau principle and we showed that there's 1s and then there was 2s, and then we showed that the 2p was actually substantially higher in energy, and that had to do with orbital penetration and shielding effects, screening effects, I think maybe I might have said that as well. So if you're trying to remove or ionize an electron, the ionization of the electron is directly related to where the electrons are in the orbital. So if you're looking at a 2s and you want to take that electron out, it's actually further down in energy than the 2p. So if you're trying to take the 2p out, it doesn't take as much energy, and then the result is the ionization energy is actually a little bit lower than trying to take it from a 2s. So when we go back and look at this trend between beryllium and boron, this is associated with essentially what they call the cost of opening up and putting an electron into that higher energy orbital. Now, once you have the higher energy orbital open, right, you're also adding effective nuclear charge, and so the trend, now that the orbital is already open, just continues to go up until you get to nitrogen. And that's actually what you're seeing between magnesium and aluminum. You're going from a situation where you have an S2 filled S subshell to just opening up the subshell for P1 in aluminum. All right, now going to the N, the nitrogen and the oxygen, right? That was the other place we saw the anomaly. That is between, I've got all these windows open, between nitrogen, oxygen, and phosphorus and sulfur. And so what's different? That oxygen is lower in ionization energy than the nitrogen, and sulfur is lower than phosphorus. So to understand that, again, we have to go to electron configuration. So we go to oxygen. And oxygen, I'll just write the whole thing out. 1s2, 2s2, and then it's 2. Well, actually, I should do nitrogen first because it's left on the left side. 2s2 and then 2p3. For oxygen, it's 1s2, 2s2, and then 2p4. Now, it doesn't look at first like there's anything significant going on here, but what if you draw the orbital diagram, right? When we do the orbital diagram, and now I'm just going to do the valence electrons, I have 2s and 2p, and then over here I have 2s and 2p. I have 1, 2, because I have the 2 that fill it, and then 1, 2, 3. So that's a half-filled subshell. And then for oxygen, it's this. And what do I have to do? I have to add an electron here. And what I've done effectively is paired electrons. And I have what's called, again, electron-electron repulsion. And so in terms of energy, right, because the electrons are repelling each other, this electron who was already in the room to start with is telling this one, hey, I want you out of here, and it actually helps it to get out. And so when you go back to the electron configuration, here's, right, or the ionization energy trend. Nitrogen's up here, oxygen is down here because of the electron-electron repulsion pushing the electron out. Now, having said that, another thing that's going on here is half-filled subshells tend to be a little bit more stable, and by more stable, we say they're lower in energy, and the oxygen disrupts that stabilization by putting an extra electron in that half-filled shell that was from nitrogen. So the nitrogen's a little bit more stable because it's half-filled. The oxygen's less stable because now we have electron-electron repulsion. Now the trend still goes. It goes from oxygen to fluorine to neon, right? Because effective nuclear charge is still going up. And we see the same thing in phosphorus and sulfur, and we see the same thing in the fourth and the fifth periods of the periodic table. Okay, so now what we wanted to do is we want to look at what happens. We've looked at first ionization energy trends, so now we're going to focus on individual elements and look to see what happens when you ionize them successive times. That is like more than once, right? So 2, 3, 4 times. Okay, so the first ionization, this is essentially what I had up on the screen before. The first ionization is this reaction, second ionization is this reaction. Basic rule, right, is successive ionizations cost more energy. So every time you try to take off another electron, it's going to just cost you more energy for a couple of reasons. You're left with a positive charge after you take the first electron, and so the atom actually shrinks because there's less electron-electron repulsion. Remember, cations are smaller than their corresponding atoms, which also means the electrons are closer and more strongly attracted. And the more strongly attracted just means the ionization, second ionization energy will be larger. So what we're going to do is look at magnesium first. Okay, so here's magnesium over here. Pointer's not pointing. Great. There it is. There's magnesium here, right? First ionization 738, second ionization 1450. Now, if you think about Coulomb's law and you're just basically like doubling charges kinds of things, you're increasing charge. It's kind of what you might expect, right? It's an increase, it's substantial, but it's not this crazy one that you're seeing behind it. Now, look at what happens to sodium. For sodium, the first ionization energy is 496, which you'd expect relative to magnesium, because magnesium's ionization energy will be higher as a result of increasing effective nuclear charge. Again, the whole Coulomb's law thing. But look what happens after its first ionization energy. It's roughly 10 times. And then the third ionization is also very large. But you expect the increasing ionization energies. But what you don't necessarily expect without thinking about it is that the first ionization, second ionization, also the third ionization is way bigger than the second ionization. And why isn't the trend like more uniform? And the simple answer is the first ionization energy is what you expect. The second ionization is what you expect because you're removing electrons from the core of sodium rather than from the valence shell. So if we write the electron configuration for sodium in core notation, we have neon, and then we have 3s1, third period element, right? And what happens is you're trying to take this electron off. That's what gives you the 496. But when you're taking the next electron off, this big jump is you're trying to take it off the noble gas core. Remember, these cores are much smaller than their corresponding atoms. So in essence, you're suddenly much closer to the nucleus, having to pull electron much further out to get it out of the atom. Now for magnesium, its electron configuration is this. Again, it's right next to sodium, so we would expect 3s2, right? Because it's the one right over next to it. First one comes off, you're good. Second one comes off, you're good. Now the third one would have to come out of the noble gas core, and again, there's this giant jump in ionization energy because you're now removing core electrons, and that's what normally we see. So here's a listing. Oh, by the way, so if you see where the jump is, right? The one right before it's the number of valence electrons in the atom. So you can actually tell, like looking at ionization energy trends for successive ionization energies, what group the element comes from. So here's just a table. Successive ionization energies for elements sodium through argon. Again, this is the value we saw for sodium, or roughly similar anyways. And then this is magnesium. For aluminum, remember, aluminum has 3 valence electrons, so the next one's just out of the world here. And then the fourth one for silicon, phosphorus is the fifth, and sulfur is the sixth. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So this one is for sulfur, is the 7th electron, but it has 6 valence electrons. And so that's why this one is high, but then this one's way higher. Now, why are the core electrons so much harder to remove as you're going from left to right? That's because the effective nuclear charge is higher. So effective nuclear charge is still going up as you're going from top to bottom on this particular arrangement of the elements. So the result is as you rip electrons out of the core, the ionization energies also get bigger.